Well, hello. Is anyone there? This is Mr. King. Good morning, Megan.
Good morning. How are you?
Good. How are you doing?
Good.
Good. Welcome back. Happy Tuesday.
Thank you.
How is your math coming along?
Pretty good. I tried to log in yesterday though for your office hours.
Oh, you
And I
know
don't.
what? I was a bad person. I didn't have it yesterday.
Oh,
It
okay.
was really by accident. I was studying some things and I lost track of time and I didn't have it. But don't think that I don't normally have it, okay? Because I normally do.
No, that's okay. I'll try again tomorrow. I'm
Okay,
okay. I just have a question about the other homework for the other class, and it's on matrices.
okay, okay, very good. Okay, well, let's begin. We're gonna cover two sections, hopefully, and they're kind of nice sections, so I think it should be relatively nice. But one way to find out, I guess, okay?
Mm.
So here we go. And we have Griselda with us.
Good morning.
Good morning, Griselda. How are you?
I'm fine, thank you.
Good. How's your math going along?
Well, I've been trying to catch up. I've been catching up with Ferguson's, and I just have one. I think one with you that I need to turn in by tomorrow.
Okay. Were you able to catch up with her class okay?
Yes, I just need to start doing quizzes.
Okay. Well, you're on the right track. So keep it up, okay?
Thank you.
Okay, so let's begin. We're going to look at section 1.6 and also remember there's a quiz there. Speaking of quizzes, there is a quiz over sections 1.1 to 1.5. 1.1 we didn't actually cover, but it's very basic, just like drawing a point and identifying a quadrant. I don't know if can you all see the WebAssign graph here?
Yes.
Yes.
So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So as you go in counterclockwise direction, so this is just 4 little squares here, but they go on forever. So they call them quad for 4, and someone just decided to name them quadrants. So this is 1, 2, 3, and 4. So the only question that looks a little bit maybe intimidating is if they said something like this: if x is less than 0, well, that already is the clue, and that's going to eliminate at least some of the quadrants. So if we're playing a little investigator here, detective here, and they're saying the first dimension, here's the tip pointing to the variable. So it's saying x has to be smaller than 0. So, and we know this is the x-axis, of course, then which way is our x is less than 0, of course.
The negative numbers.
Yeah, so doesn't that mean it has to be one of these two? This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So aren't these two quadrants already eliminated right here? Because in these quadrants, x is a positive number, and they're telling us that x has to be less than 0.
Yes.
Yes.
Is that okay?
Mm-hmm.
Yes.
So then they would give you one, because right now it could be quadrant 2 or 3. I just making up an example. And then let's just pretend the other clue is y has to be less than 0. So both of these have to be followed. So even though you picked this one first, it wouldn't have mattered if you would have picked this one first. You just would have eliminated maybe a different, some different quadrants. But in the end, no matter which clue you use first, you'll get to the final quadrant that's left over. So if y, the dimension or the y values have to be, the tip again is pointing to the smaller side object. So y has to be smaller than 0, which means again negative. So now we're looking at the y dimension, of course, and which y, so where do we have to be if y is less than 0? Is that upward or downward, of course?
Downward.
Down.
Downward. So now, isn't this quadrant now eliminated as well?
Yes.
So then you would just write, if a point is less than 0 and the x is less than 0 and the y is less than 0, then the point has to be in quadrant 3 somewhere. And then you would just write, click the right box, quadrant 3. And they like to use Roman numerals for some reason, not sure why. That's 3 in Roman numerals, okay? And 5 is the V, and if you have, this is 1 before 5, which is 4, and so forth. But you only have to know Roman numerals 1, comma 2, comma, here's 3, here's 4, and here's 5. Well, you don't need 5 either. But anyway, 1, 2, 3, or 4. So any questions with that?
No.
No.
Oh, we have someone else here. Oh, let's see. William. Okay. Hello, William. He's coming. Takes a few seconds. It's kind of amazing, actually, how all this works. Hello, William. So let's continue. And that was just a little, really, that's the only thing that would have been slightly new, if at all. But I hope that makes sense, okay?
Yeah.
And we lost William. Hope he comes back. Okay, so let's go on, and so I'm gonna clear this out. So here we are. I wanted to start with this problem on section 1.6. So here we go. So, oh, let's see. Megan, can you read this? Because my voice, I get tired. I'm talking for all these hours every day.
Oh, I'm sure.
And I get to hear you. We get to hear your voice as well. So.
Write the linear function f that has the given function values.
Okay, so we are given 2 points and we get to graph it and then write the equation. And they tell us it's linear. So it's not like, oh, you wouldn't know which of these toolboxes to click here because they tell us it's linear. So we're gonna, how about we draw it first. And hello, good morning, William.
Good morning.
How are you? How are you doing?
Good. How about you?
Good, thank you. Is your math okay?
Yeah, it's doing good.
Good. Okay, so we're gonna plot these 2 points. So we go to line, because it tells us it's linear, and we simply draw the points. So one of them is 1, 7. So Megan, which one is this? One of these is a domain value and one of them is a range value, or in other words, one of them is an x value and one of them is a y value. Which one's the x value?
1.
1, and then it maps to what? Range
7.
value what? Or y value what?
7.
7. Is that okay?
Yes.
So you just, if a person's not used to that notation, this is the domain number or representing the, one is one of the many potential domain numbers from the first dimension, from the x-axis, and it's telling us at x equals 1, it must be in the domain set, the domain bag, because it maps to, it has a mapping onto its graph, and it maps to the second dimension value, which is the y value, the range value, and it's 7. So this is just another way of writing this like this, 1 comma 7, or in an ordered pair notation, 1 comma 7. So these three are just different ways that represent the same thing. Okay, so we just plot the point, and so 1 comma, whoops, gonna make sure I put it in the right place. And then this graphing tool knows that it's, well, we already clicked lines. So as soon as you click a second point, it's gonna connect those 2 points. So the second point would be what domain value, Megan?
0.
And what does it map to? Here's x equals 0, and it maps to what?
8.
8. So where's that? Left, right, up, down? So
Just up 8
just up 8.
on the way.
Mhm. And there's our slanted 2-dimensional line, and that's one part of the question. And they don't tell us that's an inequality, which would then mean we would have to decide what other, if it's this set of infinitely many points that are also solution points, or this side, it's not a linear inequality, it's just linear only. So we know it's just these points on this line right here are all the infinitely many solution points. So yeah, any questions there, guys?
No, sir.
No.
And now we want to come up with the equation. Well, if they happen to by luck, or maybe they did it on purpose, so remember, this is probably of the different forms of a line, the most common one, or the most used one, there's really 2 of them. I guess it's kind of hard to say which one's used most, but the 2 that are used most, let's put it that way, is this one up here and this one right here. And hey, I'm getting better with this mouse, I think. This mouse stylus here. Anyway, you guys are supposed to say, yes, Mr. King, you're getting better, okay?
You are getting better.
Oh, thank you so much, Megan. Appreciate that. Okay, it's almost legible now, okay?
It is.
Oh, it is. Oh, see, extra credit for Megan, okay? All right, so this one, what was this form called right here? What does the M stand for again?
The slope.
The slope. And the B stands for?
The y
Y-intercept.
intercept.
And this is the y-intercept point. And the B is not the entire point, it's just the y value. It's where it touches the y-axis. The line touches the y-axis. And then we could also just write the whole entire point down. So much for my nice writing. And then my hand gets tired. I'm such an old man here, I think. Anyway, this one here is also slope. We're going to use this equation on the next problem. So that I'm also just want to take care of this as well. So slope, just like this one. But instead of having this one, you'd have to know the y-intercept and put it right here. And for this form, you still have to know the slope, like up here, but then you would need, in addition, plus 1 extra point on the line, plus any point on the line. So this one, you have more options, the second one, because if you know any, you don't have to know the y-intercept. If you do know the y-intercept, you could still use it on this form, yeah, and put it right here is the any point is denoted by x1, because it's like 1 point, one of the infinitely many points that is on the line. So x1 comma y1, that little subscript 1 just means it's 1 point on the line, and it could be any point. So this one's more specific. It's a point on the line, but it can only be a very special point, and that's this one right here. So where the line touches the y-axis, that point right there, that number, which is the 0.08. So if we wanted to, you could take this 0.08 and plug it in. Right here would be 8, and right here would be 0, and put the slope here, and you get the same answer as if you did it up here. And you can tell why, because what's going to happen right here, class? X minus 0 is just going to be what right here?
X.
X, and then it would be m times what?
X.
X, and then how would you move this negative subtraction of y1 to the other side? What's the inverse of subtraction of y sub 1? It would be what?
Addition.
Addition, and then over here it would be plus, huh?
Yes.
And then instead of y1, that if it's the y-intercept, this would always be the y-intercept number, like the 8, and then it would move over to this side and be plus, and then the y1, but that y1 would be, if you use this one up here, it's just the y-intercept number all the time. So I hope you can see that if you took the y-intercept and put it into this equation, it's really the same thing as this. This is just a shorter version of this one down here. So you can only use the shorter version is if you, and come up here, is if you know the y-intercept point. So I don't know if that makes sense, but any questions about that?
No.
So anyway, so let's see. We could use this form to write this linear equation, or we could use this form. Really, it's our choice. How about on this one? Because do we know the y-intercept? Did they happen to give it to us here? Is it one of those 2 points we know?
Yes.
Yeah. So how about we just come up here then and use this one for practice sake. And on the next problem, we will use this one down here, because it turns out they do not give us the y-intercept. That's this one down here, number 12. Anyway, so here we go. Well, so if we write the linear equation, we're going to use this form right here. So it's going to be y equals, and the slope times, this is a slanted line, so it has to have the 2-dimensional variables, y and x in it, and there they are, plus the y-intercept number, not the entire point 0,8, but just the actual y value, the range value where the line touches the y-axis. And Griselda, what number is that again?
8.
8, good. And now we're just need the slope. And whatever it is, you put it in right here. So to compute slope, we practiced this in the last lesson, and we could do it 2 ways. We can find the slope with rise over run by counting on the graph. If we have 2 simple points that are clearly visibly on the, I mean, if it was somewhere like in here, you wouldn't know for sure what value it is. So then you would be risking it by trying to do the counting. But here it's clearly, plus they gave them to us, so that's even more obvious. But here we can safely count, yeah? So we can use rise over run, remember, and that's counting. So this would be if you just want to count and look at the graph, counting. And the other one is as a formula. And does anyone remember the formula or have it handy?
It's
Y2 minus Y1.
Good. And that's the difference between the Y values. Y values are up and down, vertical. So that's the rise part. This is not counting. This is just doing the same thing as counting, but by computing.
Mhm.
Computing using the formula. So either one will do the job. So if you don't have the graph and if you don't have the graph and you just have the 2 points, well then unless you want to graph the 2 points and then count, but it would have to be, you want it to be on graph paper or something, or just make sure you could count correctly. Well, then otherwise you might as well just use the computing formula instead. And then what was the denominator then for the run?
X2 minus X1.
Mhm. So either way, we could find the slope, but since they're clearly right here, we can count, yeah? So Megan, which point do you want to start with? Doesn't matter.
The 0, 8.
So we're going to start here, and then we're going to move to this point that we know. If you want to, we could pick another point. I mean, they're going to be bigger numbers. Rise and run will be bigger numbers because they're further apart. But when you write them down, you would be able to reduce them, simplify that fraction, and it would be the same number as this one if we use these 2 points, as long as we counted correctly. Does that make sense?
Mhm.
Okay, so, and which way do you want to move or count first, Megan? The rise, the run, it's up to you.
The rise.
And so the rise is either upward to get to this other point, or it's a movement downwards. So of course, so let me write it up here. So slope equals, so what's a downward movement, Megan? Positive movement or negative?
Negative.
And how many units is it only if we want to go here and then here to get back onto the line? So it's how many units down?
-1.
Mhm.
And
then the
positive
run, and you said positive 1?
Mhm.
And that's it, yeah. And just for example, if we wanted to pick, let's say you pick this point, that's the x-intercept, by the way. William, how many points, no, how many units would it be from here all the way down to here, which would be the rise, and then we would do the run. What would be the rise from here, William, down to here?
-8.
Mhm. So if we would pick a different point, or even 2 different points, we will, unless we make a mistake, we will get the same answer. And that would be the rise downward 8, -8, and what's to the right, William?
+8.
And what does -8 over 8 reduce down to?
-1/1.
Yeah. So we get the same thing. So I hope that makes sense, everyone. Okay? Any questions there?
No, sir.
No.
So now we just put our slope right there, and if there's something to clean up, we clean it up. Well, -1 times x, I mean, you can leave it like that with a parenthesis, but you don't need to. And you don't even need, because it's multiplying by -1, if you just want to say negative x, that's the same thing. So either way. So we can type that in right here now. Okay, any questions?
no, sir.
Okay, so going to do that here. And we have f of x, which remember means it's a function. And this is a function, right? If we go along the domain axis and stop anywhere, it only has one mapping for all of these domain values. So, excuse me. So here we can put negative x, negative 1x, it doesn't matter. It's the same thing, plus 8. And we check. And there's a nice green check and a nice green check. So that means we're good. Any questions here?
No, sir.
No.
Okay, so let's erase this business and then we go on. And I wanted to do this one next with you. Maybe I shouldn't have erased all that, but you still have it on your, well, I don't know if you guys take notes here while we're working or look at it later, or what do you guys do?
I take notes.
Take notes?
Yes.
Okay. Do you guys have to go back to the videos on Blackboard at all, or you usually don't?
Sometimes.
No.
I don't.
You don't, Megan?
No, I just use my notes.
Okay. William?
No, I don't have to.
Okay. And when you don't join in, do you go and look at the video?
Yeah.
Yeah. And then you can fast forward or whatever if you need to.
Yeah, definitely.
Okay. All right. So let's continue. So right here we have number 12. William, can you read this, please?
Write the linear function f that has the given function values.
Great. So it's the same question as up here. It just there's no toolbox to graph it this time. Instead, we match. And then we still write the equation. And it's still linear. So, well, first let's just match it. So they give us a point right here and another point right here. So, William, what's this right here? It's giving us a point, and what point is that right there, William? If we wanted to write it as an ordered pair form.
-4, -5.
Mm-hmm. And that's 1 point. And we could call that the first one, or it doesn't matter which one you call the first one. So, and what's the second point, William?
1, 2.
Mm-hmm. So you don't necessarily, of course, if we're comfortable reading it like this, then when there's no need for us to write it down in another fashion, but we certainly can. X, 2, Y, 2, and yeah. Okay, so we simply now look and match, which graph. So let's see, -4, -5. And that would, by the way, we talked about quadrants at the beginning of the class. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So quadrant 1, 2, 3, and 4. So this may or may not be the correct graph. I'm just using it. So that's like a 1 with a V, and that's 1 less than 5, which is a 4. What happens, William, when the X dimension is negative and the Y dimension is negative? What quadrant would we have to be in?
3.
3, very good. X is negative, that's this way. Y is negative, that's downward, so it's here. Are there any questions, ladies? The other two, which are ladies, any questions on that part, that logic?
No, sir.
No.
Okay, so let's start to rule out answers. So William, you said quadrant 3, so very good. This is -4 and -5 is right here. So that looks believable. that it's on the line. So we can't cross this answer out yet. And what about this one, William? This is -4, -5 is right down here again, but is there any line here?
No.
So this one's out. It cannot be this one. So this one's out. We rule it out. It's eliminated. And so forth. And oops. So what other one can we eliminate here then, William?
The bottom right one.
The bottom right one. Very good. So, and this one's out. So that means it's one of these two. And then what else should we do now, William, of course, to decide which one does it have to be?
Compare the two?
I'm sorry?
Do you compare the two?
Compare the two. And do we have any other information that we can use to compare the two?
The 1, 2.
Ah, there you go. So let's see. What about this one right here? Well, this looks like it's how many units over? Well, if you go 1 over, I should say, and go 2 up,
Mm-hmm.
does this one look like it? Does it look like the 0.12 is on the line?
Yeah.
Yeah, so that's possible. How about this one, William? This is 1 over, but this is only how far up right here?
Just 1.
And up here would be 2. So this point is, this graph here, it can't be because here's 1, 2, and it's not on the line. It's close, but it's not on the line. So this one's out as well. So it did turn out to be this one, but anyway, so that's that. So we could check it, but let's just write the equation. And now, so William, well, did they give us, I mean, right here is the y-intercept, but do we know for sure what this number is right here, William? I mean, person might say, oh, it's 0.5. Or somebody might say, no, it's 0.51. And then Grisela might say, no, it's 0.52. And then Megan might say, no, it's 0.60. And then you guys start to fight over it, yeah? And who's correct? So, but the point being, do we know absolutely for sure what number that is right there?
No.
No, because that's 1, that's 2, and it may turn out to be a half. It may turn out to be 0.5, but we can't say for sure, yeah? So therefore, since we do not know the y-intercept, which of these two forms can we use? Well, there is actually a way to use it, but I'm not teaching it that way. I'm not showing you guys how, not to be lazy or rude. It's just that I want to keep these distinct. So there actually is a way to use this to figure out the equation of the line, but I don't think it's a safe way when you're teaching a lot of people. So I would rather teach it and understand the distinction, the differences when you would want to use this line, I mean this form of a line and this form. So that's just my personal preference in that I'm trying to keep unnecessary confusion away from people who are learning it. If someone wanted to ask me individually, how could you also do the problem, this one, with this form up here, I would be happy to show them, but I wouldn't want to show it to a whole class unless it was already past this level and we were on the next level class or something, okay? So anyway, so having said that, this right here again is what, William? This represents what right here?
The y-intercept?
Good, and do we know the y-intercept for sure?
No.
No. So then we should use this one, huh?
Yeah.
Because what's this require? It requires, just like this one does, both of them require us to find the what?
Slope.
Slope. This one though requires that you know the y-intercept, which we don't. And this just requires that we have what? What's this x1, y1 represent again, William?
Just any ordered pair on the line.
Any ordered pair that's where?
On the line.
Very good. Don't we have, actually we have two of them right here that are on the line, don't we?
Yeah.
So we could use whichever one of these we want and put it into this one. And someone might say, well, won't it make a difference? And the answer is the work, when you start to simplify it, it'll look different if you put this point in and this point in. But when you get done, it simplifies down to the same answer no matter what. Because this should work for any line on the point, provided you have the correct slope and you don't make any mistakes. So, okay, so let's see here. Well, let's find the slope. And we could count. We do have this point right here. And we have this point right here. So counting it, the rise and the run is certainly possible. And not only that, it's nice. If we did count, I do want to practice using the formula though, just for learning purposes, but we certainly could count. Or we can also use this, y2 minus y1 over x2 minus x1. So what if we counted, let's see, Griselda, if we counted from here to here, which point do you want to start counting from? This lower one, the higher one? It's up to you.
The higher one.
And then we're going to go down to this one. And
Correct.
do you want to do the run first? Left, in this case, it would be left. And then do the rise? Or do you want to do the rise first? That would be this way, and then the run. It's up to you.
I did the rise over.
Okay.
Run.
So what kind of movement is the rise? It's with respect to the y dimension. So is it positive or negative?
I went down, so it would be -7.
Very good, because this is 2. So from here to here is 2, and then 5 more makes 7, but it's -7, huh?
Yes, sir.
And then the run, so that would be like this. Oops, this is supposed to be straight down. And then we'd have to do the run, which is leftward.
Which is 5.
And so this is 1 to here, and 4 more is 5. Good. And then that's moving leftward. What's moving leftward?
Negative.
Negative. So by counting, and then what's negative divided by negative?
Positive.
Mhm.
Positive 7/5.
Good. So by counting, we get 7/5, and we would put it right here. We could also do it by using this formula. So I would like to practice that once here. And so y2 minus y1 and so what if we practice that? We better get the same answer. And oh, so many colors, not really, not too many colors but to choose from, but how about that? So let's see, Griselda, so what goes up here? The rise, which is which variable?
The y, it would be number 2.
So what's the, so now I already named this one the second one and this one the first one. We could change it, and just like you said, start with this one and then count down to this one. You could have also started with this one and moved up to this one, but in the end you still get the same answer. So I mean, it makes sense. We have to, because it's still the same 2 points. We're trying to find the slope. So let's say we just stick with this. This is the second point, and this is the first point, Griselda. So what are we going to put right here for y2?
Y2 would be number 2.
Mhm. That's this one. And what's our first y value?
It would be -5.
Which is this one. And then what's what goes here?
1.
Yeah, now once,
The x number 2.
good. Once you commit to calling this the second point, you can't come down under in the denominator and change your mind and call this the second point, because then that will give us the wrong answer. So yes, correct. So 1 minus what?
-4.
And very good. And the reason I put parentheses here, because it's very classic error, is when if we don't early on when we're learning and practicing these concepts, that if we don't put a parenthesis, then if we have a -5 right here, it's easy for, say you have 1,000 people learning, there's going to be quite a few, unfortunately, that would just put a 5 here and say, oh, there's the negative part. And then I hope that makes sense. And we don't want that, right? It's always subtraction in the middle. And then sometimes this number here is negative and sometimes it's positive. So as long as we're careful there, then we'll be fine. Any questions on that?
No, sir.
No,
No.
So now what does this subtract negative turn into, Megan? I mean, Griselda.
+7/5.
So you're ahead of me again, aren't you? Good. So, and that's the same answer we got here. Okay. So either way, counting rise over run, using the formula, it doesn't matter which point you start with, which point you call the first point or the second point. It doesn't matter if you start with this point, if you do the rise first, the run first, all in the end, it has to reduce down to the same slope. So now we put that right here for M. And so now we're going to write Y. Megan, which one of these, that's another confusion source. There's 2 letter Y's and there's 2 letter X's. So which one do we put the actual point that we have that's on the line? For any point that we know on the line, we plug it in. So which of these 2 Y's is meant to be where you put the Y number of your point?
Y1.
Y1. And doesn't a slanted line, Megan, have to have 2 variables because it's moving with respect to 2 dimensions? Yeah?
Yes.
As we're moving up, we're also moving what here, Megan? Are we only moving up? Or are we also moving rightwards?
Right.
This is 2-dimensional movement, isn't it? You're like, no, it's just going up. Come on. No, this is just going up, vertical. And then you're not moving at all with respect to the first dimension. That's supposed to be vertical. And that's why you just get 1 letter for the equation or something. Okay, and then the same idea if the line was going this way. But anyway, so again, I'm going to put parentheses here when we insert those numbers, and just to be conservative. And Megan, what was our slope? We already had that done.
7/5.
And what goes here then? Oh, we got to decide which point. Sorry. So which point? I know this is y sub 1 and x sub 1. You can say, oh, then I'm going to use that one. That's fine. But does it, that we called it the first point and the second point so that when we could use the formula to compute the slope, we already had one of the points called the first one and one of them called the second one. And as already said, you could have switch this and call this the second and this the first. So once we're done computing the slope and we want to come back up here, it's not going to matter. This just means one point on any one point that we know is on the line. So if William used this point and Griselda used this point, then the work's going to look different. But when we're done, it's going to clean up to the same line because it has to. Yeah, because it shouldn't, if you put any point on the line, as long as you're not guessing what, like if you were guessing and then you didn't, if you didn't know for sure, what is that number, what is that point right there? Well, then of course, then we're going to have different answers because we're guessing on terms of what the point is. But if we're not, then it shouldn't matter what point we put as long as it's an actual known point on the line. So Megan, so you and everyone else, we get to pick which point we put in here. So you tell us, it doesn't matter.
The 1,2.
Why did you pick that one?
Because we used that one the first time first.
Okay, I'm just wondering why. Well, also someone might say these are a little bit friendlier than this, but I mean, that's just an opinion, yeah? Okay, so what's the y value of your point that you're picking?
2.
2. And what's the y value, I mean, the x value of the point that you're picking that's on the line?
1.
1. So, are there any questions in filling this number in right here?
No,
This
sir.
point. Okay, now we clean it up. So what about here, Megan? Do we really need the parenthesis anymore? It's just is it minus -2 and then we have to change it to +2, or is it just -2?
Just -2.
I'm gonna move down here out of the way here. So we're gonna have y minus what?
2.
Equals, and this is this x minus -1, Megan, or just -1?
-1.
So 7/5 times x minus 1. Sometimes in higher math classes, when you get it like this, they just say leave it like that because that's the line. And there's nothing wrong with leaving it like that because they don't want to bother cleaning it up. But in our class, this is when we're practicing it, as well as a couple of earlier classes as well. And then the emphasis was just concentrating on this and now and cleaning it up. So we are being asked to clean it up as well. So so let's see, Megan, what should we do to clean this up anyway? We want to have y equals, because that's how they ask us to do it. So what has to be moved for sure?
The 2. The -2.
And how do we get rid of a subtraction of 2?
Add 2.
So we could do that, and we're going to have to do that. We can also, they don't tell us to multiply this through. So we probably could get away with not and just write equals 7/5 times x minus 1 and then +2. But at this class level, they do want us to practice multiplying this through. So let's do that. So Megan, what's going to happen when we multiply 7/5 times each term here? So what's 7/5 times x?
7/5 x.
And 7
-7/5.
7/5 times -1 is -7/5. And I did skip a little step here, but hope that's okay. And what did we say we were going to do to get rid of this subtraction of 2?
Add 2.
Add 2 to both sides. So that goes away, add 2 over here, and then we get +2. Any questions on that so far?
No.
Now clean up, if possible, these three terms. So can 7/5 x be combined with any one of these other two terms, Megan?
No.
And why is that? Because I'm not sure, Megan. Help me out.
Oh, because it doesn't have a variable x.
Ah, very good. So none of these have an x to the first or x to the first, so we cannot combine it. Do these two have any x's next to it?
No.
So these are like terms, aren't they?
Yes.
And now we can combine these two, but it's a fraction plus 2. We could use a calculator or something and have the calculator do it for us, but I know Megan loves fractions, so we're gonna do it by hand here. Right, Megan?
Oh, yes.
Okay, very good. So plus 2. Megan, what can we always put underneath a number without changing it, its value?
A 1.
A 1. And we want to add these two together. And so the common denominator between 1 and 5, what's the smaller denominator? 5, 1?
1, but we're gonna make it 5.
Yeah, because 1 fits into 5, doesn't it?
Yes.
So the common denominator, the smallest number that 1 and 5 both fit into by multiplication is the 5. Because 5 times 1 is 5, so that doesn't change anything. So if you're not changing this denominator, you're not changing the numerator. Or you could say I am changing it times 1, but times 1 doesn't change it anyway. So what about this one? It does change. 1 times 5 gave us the 5. So then we have to do what to the numerator, Megan?
Multiply it times 5.
And of course, that's what?
10.
And now we have, excuse me, we have -7 plus 10. So what's -7 plus 10?
3.
3. And there is this part here combined. And notice, that's a positive 3/5. So Megan, what happened when we took this form right here and we inputted the slope 7/5? We put 1 point in. If you would have put this point in instead, this would have looked different throughout all this computations, but in the end, you would have gotten this as well. And now, what form is this in, Megan? This looks familiar to me. What form is this one?
Y equals mx plus b.
Very good. So what is, this is the m, huh? And this is the b over here?
Yes.
So, so the slope is 7/5, which we already knew. And what's this part right here tell us, Megan?
The y-intercept?
Ah, so that was way back here. And remember when we were arguing and you guys were starting to wrestle and fight? And some of you said it was 0.5 and someone said 0.51. And then a cat walked into the room and said it was 0.6. And that cat was right, you know, that 3/5 is the same as 0.6. So we should listen to the cat, I think, huh? No, I'm not, I know I'm not being funny, but anyway, so any questions here?
So how would you, actually, I do have a question. How would I do it this way? Like, since both of them are fractions now, how would I line it up or put the line on the fraction form?
Oh, you mean if you had to graph it?
Yes.
So if we had to graph a line like this, that was given to us in this form, huh? Yeah, that's a little more challenging. It's not impossible. It's just gonna be, let me put it this way. When we say impossible, I guess it depends on how we interpret impossible. So you are right, Megan, there would not, and I'm gonna clear this scribbling out, okay? Because, yeah. So first of all, let's just type this answer in to make sure we're correct. So I wanna do what here? Oh. So just type in 7/5 x and then plus 3/5. And then we'll answer Griselda's, that's a good question. And here's the one, and here's the green check. So that is, so we're correct. And now let me clear this mess out. Okay, and now let's again say you were asked to graph this. So, very good question. It would be on this graph paper, Megan, Griselda, 3/5. It would be impossible for us to know exactly where 3/5 is, wouldn't it?
Mm-hmm.
So would we be able, on this graph paper, just as it's labeled, would we be able to do it exactly or approximately?
Approximately.
Unless WebAssign, there was a box right here, and then they let us, sometimes they let us put the points in somewhere, but then you would type in the 3/5 or something, and then that would be a way if they let us type in points or something. Otherwise, the only other way you could graph it precisely is if your graph paper had right here, not 1, not 2, not 3, and so on, but 1/5, 2/5, 3/5, like that. And then the same thing this way, 1/5. Does that make sense?
Mm-hmm.
Then we could draw it up exactly. But otherwise, it would be an estimate. I don't know if I'm answering your question.
Yes.
So as an estimate, pretend then as an estimate, Griselda, then we would do what? What's the y-intercept?
3/5.
3/5. Where is that? About right here. This is an estimated graph, meaning we cannot know exactly where 3/5, which is 0.6, by the way. And now we would count. What's the slope here, Griselda?
7/5.
So maybe this is more of what you were asking. 7/5. And now we would move and to get a second point and then connect it. But it would be an approximation. Now, let's say I do have lines here, 2, 3. Oh, I'm going to have to go up a little ways here. So just pretend that, and then over here is 5. Okay, so then here, Griselda, we would go up how many units? Let's say you did the rise first.
7.
Go up. So now that's not 1 unit. From this little point to right here is not 1 unit, is it?
No.
It's just a little piece. So you'd have to go like right up here to this kind of the same, kind of approximate and say, oh, that's like 1 unit, and then a second one, and a third one, and a fourth one, a fifth one, a sixth one, a seventh one. So it'd be like right about here, huh?
Yes, sir.
And then you would do the run, which would be what?
5.
And then you would say, oh, I'm like right about here, and I just go straight across. And then now you have your 2 points, and then you would take a ruler or something, which I'm gonna destroy, but just pretend that that would be the line.
Okay.
Does that make sense?
Yes, it's just it confused me when the y was a fraction. I didn't know how to start from there.
So did I answer your question?
Yes, sir.
Okay.
Thank you.
You're welcome. Any other questions here?
No.
No? Okay, so let's go on. And so the next thing I want to show you, well, let's see. How about we go up to the top? And there's some questions here that are kind of quick. Number 4, and some of these we've dealt with already throughout the semester. There's 1 or 2 that we haven't. But what is this? What kind of a graph is this class right here? If there's anything with the highest exponent 2, then is it linear? So you've heard me say this a lot. Is it linear when that's a square?
No.
No. To be linear, it has to be a what?
A 1.
A 1. And what happens when it is a 2? Well, if both of them were 2, then it's a circle. But this is just y right here. This f of x is just y.
A parabola.
A parabola, good. And then there's a name for that type of equation. We say it's a parabola. So this equation has a parabolic graph, and that's mathematically correct to say it that way. And then another way is to say, there's actually some different words we could use. What power is this? This is a power function, but what power?
Square.
Square. So which of these because there's a few close ways of saying the same thing. So which one here is the closest thing, or which is a correct way to say it? It may not just be the exact word that we just used.
A squaring function.
The squaring function. Okay. Any questions there?
No, sir.
And this one? Is this a power function or a root function?
A root.
Root.
And what's this invisible root right here?
2.
2. So root 2. If they would have said here, this is a root 2 function, that would be mathematically correct. They might have used different language, and their language is just as correct as our language. Which one here is the same thing as saying a root 2 function?
A square root
The
function.
square. I guess it's just the bottom one all the time. I'm just kidding. I don't know. Any questions there?
No, sir.
So it's this one, and let's go, oops, and now let's keep going. So some of these do have new names. Well, this one is y equals some number only. There's no variable x, which means it's not a two-dimensional moving line, so it's not slanted, and that means it's either moving left and right only or up and down. So pretend it was like y equals 4. We're supposed to say to ourselves, that's only has one variable, y, and it's to the first power. So this is not a slanted line. It is a line. It's just not moving with respect to two dimensions, both dimensions. So it's either moving up and down only, or moving left and right only. And this was the rule that gives it away. It's supposed to. It's saying, hey, if you're cruising on, you're going on a vacation and you have to follow this rule. You have to stay on what y value?
4.
4. Sorry, that's all you get. Okay, because you bought the discounted price for the holiday, and therefore you don't get to go anywhere here. Sorry. You only get to be where in the y dimension is always 4. So does that mean you're stuck right here only and that's all you can travel?
Yes.
You're just stuck at that one place. So you're sitting in your room and you can't even leave the door. That's it. Or can you walk out of there? Can you walk up?
No.
Because then you would be like at y equals 5. Sorry, can't go that way. Can you go down?
No.
No, sorry, because now you're at y equals 3 or something. So you can't move slanted because now now you're also up at 5, or if you're slanted, you're down at 3, or so forth. What if we move left?
Yes.
Yeah, because y is still what? If you're right here, now you left your hotel room, and now you're still at what y value?
4.
4. That's okay. And same thing this way. So then this is what kind of line? Vertical or horizontal?
Horizontal.
Horizontal. Yeah. So this is a horizontal. This is for now. C could be any number on the y-axis here. So this really represents a horizontal line. If they said horizontal line, that would be correct, but they didn't say horizontal line. So they were more general, more vague than even saying horizontal line. And they just call it,
Constant function?
Yeah, constant. Because this represents any what? C represents any constant. And really, we could even do a better job than their choice. I don't mean that disrespectfully, but relative to the publisher here, but really it's any constant on which axis for this one. It's
Y.
it could be any constant only on which axis?
The Y.
The y-axis. It could be y equals 4, or y equals 5, or y equals -10, or y equals 0, like that. So, but anyway, any questions there?
No, sir.
No.
So that's that. And we could check, of course. Now, well, what's this one? This one we've talked about, not a lot,
Absolute.
but a little.
Yes.
What are these
Absolute value.
Absolute value, yeah. So that one. So you just kind of have to remember that. It's not. And this one? Is it a root function or a power function?
A power function.
And what
Power.
specific power?
Oh, cube.
Cube, huh?
Cubic.
So then it's not a cube root function. Yeah, that would be that would be cube root would be root symbol. But then not what right here you'd have to put a what? If it was
A 2.
2.
well, it's a 2 if
Oh,
there's
3.
nothing. But if it was cube root or
A
root
3.
3, if it was, I'm just making up an example. If it was cube root function, or there's other ways to say it. You could say root function root 3. Well, then it would be this. But this is power, and so they could have wrote a power function, but they were more specific, and they said what power? The cubing power, or just cubic. So, any questions there?
No, sir.
So that would be that one. And then, so, and this one, guys, what can you always change f of x to?
Y.
Y.
Y. Y equals ax plus b. Well, that looks kind of
A
familiar.
linear function.
Linear. Very good. What are we used to? Not ax plus b, but what?
M.
MX.
mx. They just used a different letter to mess with us, you know? And, but it's still, this still represents, even though they didn't write an m, but this is still y to the first, x to the first. So that means linear. two-dimensional linear, which means slanted, not vertical, not horizontal, but slanted. And so anyway, so this just happens to be slope y-intercept form of a line, but they don't ask for that specific language. They could have, but so they're being more vague, more general. And I'm not saying that's a good or a bad thing. That's just what they're doing. So clearly, which one of these would be the right one here?
The last one.
The last one. And you're like, what about that one? Constant. Well, that's when you have y equals only some number, or, oh, actually, it can't even be this one. It can't be this, because then it's not a function. Because if remember, if you had x equals, say, -2, one letter, it's linear, and now you're going on vacation again, you must think I'm kind of crazy or something. But
it would
you think I am going crazy, Grisella?
be no, sir.
Yeah, I heard you. You thought you were on mute, and you said he is crazy. That was not very nice. Okay. Which way can we only move, Griselda, if you have to follow this rule? If not, you have to pay more fees than your vacation.
Just vertical on -2.
You can only move upward or downward. That's supposed to be downward. And now remember, we talked about function several times now, and to be a function, what has to happen? For any value that's in the domain bag, there's only one number on this graph that's in the domain bag, and that's x equals -2. There can only be one mapping. But at domain value -2, is there only one mapping, guys, or is there an infinite amount of mappings?
Infinite.
Infinite. So is this graph an example of, this is a relation? It has it has one or more point, which makes a relation. So this is a relation, because as long as you have one point or more, it's a relation. So relation, yes, but is it a function? So to be a function, for every number that's in the domain set, when you look up or down, there has to be only one mapping. If there's not a mapping, that just means there's no graph, and that's okay. That just means that x value was not in the domain bag, not in the domain set. But this is a very unique graph, x equals any constant, because it's always going to be a vertical line, and therefore it's only going to have one single domain value. The domain bag, so to speak, would just be one number. It's just x equals -2 only. There's only one number in the domain bag. But at that domain value, it doesn't just have one mapping. If it only had one mapping, then it would be like this. At -2, then if there was only one mapping, well, maybe it would map up to here or something. Say that's a 7. And now you'd only have one point. This is a relation. It has one point, at least one point, which is just one. And it's also a function because for every domain value that has a mapping, there's only one mapping. And this one only has one domain value and only one range value. So this is an example of a relation that's a function. It's a very unique one, but this is not. This is a relation, but not a function. So kind of got sidetracked there, but I just feel it's a good opportunity to review some fundamental concepts. So anyway, so what was this one? It was like this, which is slanted line, and therefore it's not the constant function. And identity is one we haven't talked about yet. That's when y and x are identical. Identical. Y and x are always identical. This is a slanted line. It has y to the first, it has x to the first. It's 2 dimensions. It does move in 2 dimensions. It's slanted, but it only has points when the x value and the y value are identical. So if we started to make some points, William, can you give us any x value you want? William, are you still there? I think I put him to sleep, guys. Okay. Maybe he left or something. But Megan, can you give me any x value you want?
2.
So if at 2, something's wrong with my pin here. That's weird. My pin is not cooperating here. It's only letting me go left and right. It only wants to be a horizontal line. I don't get it.
Uh-oh.
So
It got burned out.
yeah, that's never happened before. Let me try again. So you said 2. Now it's okay. And then what has to be the y value if it's the identity function? Yeah. Also what? Because the y and x have to be equal to each other, which is a fancy way of saying that is they have to be identical, or fancier yet is to call it the identity function. So you'd have 2 comma 2. Would that be the only point, Megan, then? Just that one? Or could you pick another x?
You could pick another one.
Give me another one.
3, 3.
3, 3. So that would be 3, 3. And that would be a point like right here. And what would happen now? We know it's a line. What would be in it? What would have to be? Well, just one more, Megan.
It would have to be 4, 4.
4, 4, 1, 1. How about a 1.2? Is that okay? What would y have to be?
1.2.
And could we have negative numbers too?
Yes.
Yes.
Yeah, so like -1, -1. Yeah, and if you graph that, it would look like this right here. Well, pretend that I drew a line. And every single point is a solution point to this equation, and that means that the x and the y values would be identical. Does that make sense?
Yes, sir.
Okay, so that's why it's not the identity. This is not cubic. It's not constant. It's not absolute value. But we do know that it's linear, and better yet, it's a slanted line. Well, anyway, I guess it. Well, I don't want to. I'll leave it at that. So, so yeah. And there we go. So that is correct. And let's see. What else do we have? Oh, I didn't click this one, I guess. Cubic. And this one we've done. So is there anything we're missing? Squaring. Oh, this one. 1 over x. So this is y equals 1 divided by x. Now, these are 2 variables, so the function does move in both dimensions, but they are both first power, but it's not linear because this x to the first power would have to be in the top, in the numerator. So that's why this is not linear. Okay, so this is not linear. It's not a slanted line for that reason. Okay, when you write 3, what's the reciprocal of 3? You can always have a 1 here. What's the reciprocal of 3?
1/3. 1/3.
What's the reciprocal of 3/4?
4/3.
Yeah, it's like 1/3/4. But if you wanted to, you could move it up. It would become 1 times 4/3, and then that would be 4/3. Or you just, or more quickly, you just switch it and say 4/3. So the reciprocal of x, yeah, what's always underneath any object that won't change it?
A 1.
So if you reciprocate it, you're going to get what?
1 over x.
So that's this one. So that's why it's called this one, reciprocal function. Is that okay?
Mm-hmm.
Yes, sir.
So that's that one. And we could check it. So this section is going over some different things, one of which was drawing lines, understanding, continuing to practice the forms of lines, y equals mx plus b. And the other one, when you know one point on the line and you know the slope, that was called point slope form, which makes sense. You need the slope and you need one point on the line, point slope. That was the y minus y1 equals m times x minus x1. That was that. Okay, so now up here, we just answered this question. This is y equals x. So which one is that one?
Identity.
Identity. And then there's number 1 is the last one like this, and this is the most bizarre one of all of these. And this is y equals, same as f of x, just f of x tells us it's a function. And if you just write y, you don't know unless you check it, the graph or something. So this has a neat, unique notation, and x. And this is called, this one, the greatest integer function. So we just have, just like we had to get used to absolute value symbol and say, oh, that's absolute value. This is used even less in traditional math courses. But it is still an objective for this course, and it's called the greatest integer function. So that's that one. But what does it mean? So I would like, and there's problems that we're going to move to right after this one that ask us about what does it mean. So what I would like to do is just take advantage of this moment to tell us. So if we think of the number line, and we could think of it as the x-axis if we wanted to. I'm not going to do that. I'm just going to keep it just the basic understanding of the greatest integer function. So somewhere we have a 0 here. And then I'm going to write the integers down. And I'll just stop here at 4. So this is really easy if we let it be, easy, whatever that means. So this if I was a little bug here, pretend, okay, and let's say I'm just moving along here, and let's say I just stop right here, and I take a little lunch break here, and now someone asks me, hey, where are you at? Oh, I'm somewhere between 1 and 2 on the x-axis. Come join me for lunch, okay? Okay, great. So creature, a little bug somewhere from in here from 1 to 2. Now, if they asked you, your friend who you're trying to invite over to lunch says, where? And then because they're confused when you say between 1 and 2. So you decide, I'm going to tell them another way. I'm going to describe to them another way so to help them understand. And then you could say, okay, you don't understand that I'm between 1 and 2, but I'm going to tell you another way. If you're how can I'm trying to make this sound nice. I'm somewhere on this number line so that wherever I am at, when you move left, the first, and pretend like there's a road sign right here on every integer. There's a big old road sign here that says 1, and a big road sign that says 2, and so forth, and 0, and -1, and there's no road signs in between. And you would say, okay, I'm at a place on this number line where when you move left, the first road sign you're going to see is the 1, the road sign with a 1. Because if you start to move left, if I'm anywhere in here and we start to move left, the first integer that we see is this road sign 1. That means we're at the integer value 1. So what if we were right here, ladies, or in William? What would we say to help? You could say you're at somewhere between -3 and -2. But another way to describe your location would be if you move, so like if you move leftward on my road here, then the first sign you're gonna see, you'll know you're in the right area if the first road sign you see is which one? Which is the first road sign or the first integer value you're gonna see?
-3.
-3. So another way, so I'm trying to tell you in a different way, and I hope it makes sense, and then I'll use more formal language. So this represents the greatest integer function, which by the way means there's only one mapping. So any number you put in here, there can only be one range value. And it means exactly what I was trying to say. If you, I wanted to pick, sorry. How about I say this, -3.7. I'm right somewhere in here is between -4 and -3 is -3.7. It's like right around here somewhere. And that's not an integer. That's in between the two road signs, the two integers, -3 and -4 and -3. And if we're asked what's the greatest integer of -3.7, then we just cruise leftward from wherever the domain value is, and we look at the next integer, because there's a lot of integer signs. If we keep going left, there's an infinite amount. But we want the very first one that we hit, that we come to, which is why the very first one you come to versus all these other ones, this one's the greatest one compared to all these other ones, all these other integer road signs. So that's when this language of the greatest integer that's to the left of your location, or I'm trying to make it seem easier, making it real in our mind, and that is if you are at this location on this long number line road, so to speak, then the first integer road sign or integer number you will see, because there's an infinite amount of integer signs on the way leftward. But we want the first one, which is another way of saying this one right here is greater than all of these other integer road signs, if that makes sense. -5 would be the next integer road sign, but -4 is the first one, and that is greater than -5, and it's greater than the next one, -6, and it's greater than all of them. So what are we going to say is, if you're at -3.7, what's the next integer you would hit when you move leftward? Of course, it's negative what?
4.
4. Okay. Does that make sense, guys?
Yes.
Griselda?
Yes, sir.
William, are you with us? I don't know if he's there or not. Okay, but anyway, so this is called the greatest integer function, and that's the one they want us to learn in this class. There are other ones too, by the way, but this is the only one we have to learn. So what would happen if they gave us this one? And let's just, I don't know, let's see. How about -0, -0.01? So where would that be? First of all, here's 0. -0.01 is it to the left of -1, ladies, William, or is it before that?
Before that.
It's like really close to 0, isn't it?
Mm-hmm.
But it's really on the left side. It's a negative number, so it's like right here. So Griselda, what would be the greatest integer value for this domain number, -0.01? So however you want to think of it, if you like that road description that I was giving you at first, then use that. So what do you think, Griselda?
I would say it's -1, but it looks like it would be -0.5.
You're right. It would be, if there's a road sign at -0.5, then you would be right.
So it would be
But,
-1.
huh?
It would be -1.
Negative what?
1.
There you go. Yeah, so we don't get to make up new places where the road signs are, okay?
Okay.
Only at the integer values are there road signs. Or another way to say it is, more formally, is you have to move leftward until you get to the first integer number. Yeah, which more formally than that is, there's an infinite amount of integers to the left of this location, but we want the first one, which is another way of saying the greatest one, which is another way of saying the greatest integer that is left of our location. Okay,
Yes.
so either way, I hope it starts to make sense and it sounds the same, whether we use the road signs or not. Okay, any questions there? Oh, I forgot one more. What if, can anyone think of an example that I haven't mentioned yet? I mean, there's all kinds of locations, but something that would be interesting.
Fraction.
Okay, a fraction. How about that one then? Where is 1/4, Griselda? On this road here, on this number line road.
It would be on the positive side.
Good, and and I can barely hear you. It's between what two road signs? What two integers?
Between the 0 and the 1.
Good. So like right here somewhere? Yeah?
Yes.
And now what would be the greatest integer then of 1/4? Now that's very vague when I say it that way, but that's how formal language is in the mathematics, but that's when people get confused. So thinking the way I tried to make it understandable to you, how would you tell someone else that you want to teach this to, if you use my kind of language, what would you say to them? Griselda.
We would go to the left, so it would be 0.
That's as simple as that, right? It's the first integer as you move leftward that you hit, yeah? Which is 0. Correct. Okay. Megan, can you think of another example that we really haven't talked about yet that would be interesting to think of? I know I'm asking you a very vague question.
If it's 0,
Yes, if it's 0, or what else?
a positive?
Yeah.
Infinity?
I don't know.
Well, infinity would be interesting, but that's not a number, so we wouldn't be able to answer that question. That would be like undefined, because you're like, what's the next one to the left? Well,
Can we do square roots on
you
that
could.
one?
What I'm trying to get at is Megan was correct. 0 would be one example, but so would, how about -2 or any integer if you're already landed on an integer.
Oh.
Oh,
What if you're already at the road sign? Then what are you going to do? So if you're right here at 4, then you would say, okay, as you move, so this is my little description of the road is not perfect, but it works pretty well, but I have to include this last little piece. If you're already at a road sign, then you don't move, you're just there. And that's like, I'm already at a road sign, so that's it. I don't need to move. And you don't need to move to the next one because you're already at one to begin with. So therefore, if you're already on an integer on a road sign, then you don't move. You just say, hey, I'm at the road sign at the 4. So that already tells them where you're at. But if you're like right here, 3 point whatever, then you would have to go to the next integer road sign and move towards the left, which would be then the 3. So what are we going to put for the greatest integer of 4 then? If 4 is already at the road integer sign, then we just say what?
4.
4. What about a -2?
-2.
Yeah. And at 0?
0.
Because you're already there. You're already at a road sign, and in an integer road sign, or more mathematically speaking, you're already at an integer value. So you don't need to move to get to the next road sign to the left because you're already at one. You're already at an integer value. You're already at an integer road sign. Does that make sense?
Yes, sir.
Yes.
I could write a very formal, sophisticated definition, but I don't think it's necessary. You could look it up if you want, but I think it's safer, at least in the first time we ever talk about it, to talk about it this way. Okay.
Mm-hmm.
And maybe if we ever talk about this a second time, we could look at the formal definition. So, okay, any questions here?
No.
Oh, so here, yeah. It always takes longer than I think it's going to. So I guess we'll just cover this one section only, 1.6, and we have we have two ideas left, and they're pretty short, and you really have been taught them already. But before we do those last two, I want to go down here to some problems where they ask us to practice it, this greatest integer. So I'm just going to pick this one just because it's the most interesting one, because this one you just put the 4.1 into there and we do just what we were saying. So what's going to be the greatest integer value when you put domain number 4.1 in? What's gonna, so think of that road sign and where you're at on the highway, so to speak. So what would this be?
4.
3.
What would it be?
Oh, no, it would be 4.
4.
4. Is that okay, Griselda?
Yes, sir.
So 4. And what about this one? They're just trying to, well, how about this one? Negative 5.9. So then if it helps you, you would want to draw the number line and then, you know, negative 5.9,
Would be 6.
where is that?
-6.
It's like really close to negative 6.
Mhm.
So the next road sign to the left is negative 6. Is that okay?
Yes, sir.
Yes.
Okay, so that's this one. But I wanted to go down onto problem in this one, instead of just putting negative 6 in and then think about the road signs, you got to do what first to the negative 6? First, you got to add what?
7.
7.
So it would be 1.
And you, good, I heard Griselda. Negative 6 plus 7, you compute that first. And then you worry about the greatest integer answer value of the mapping. So negative 6 plus 7 is 1. And now you took a breath, you've already done the computation inside. Now you, right, or you could put equals. So what happens if you're already at an integer, Griselda? You're already at 1. So what are we going to put?
Stay there.
We stay there. Good. So the answer is what?
1.
1. Mm-hmm. So, any questions there?
No.
No, sir.
So here you would just type 1 and so forth. But I do want to do maybe 2 of these right here. And how about we pick B and D? Okay, let's do 2 of those. So how about B? And we are going to first input 2 times the X value plus 2. And then after we clean that inside up, simplify inside, we're gonna put the X value. Oh, I'm sorry, I lost my train of thought. What X value are we being asked to put in right here? What domain value?
Negative 2.1.
Mm-hmm. Now we compute, simplify the inside, and then we take the greatest integer value. So So we could do this on a calculator or in our mind. Either way, if we do go to a calculator, we would have, can you guys see the decimals now?
Yes, sir.
2
Yes.
times, thank you, 2 times -2 plus 2. I mean, we could do that in our mind, perhaps. Oh, not if you don't type it right. So 2 times
-2.1 parentheses.
negative, it was 2.1 though,
Okay.
and then plus 2 more. And so we get -2.2. So that's what goes right here, is a -2.2. And now I hope you all think this is incredibly simple, because it can be. So Megan, what's going to be the greatest integer value for -2.2? And it sounds like, again, well, I hope you understand. So which one is how would you, tell me how you say
-3.
-3. And how would you explain to me, because I'm lost, okay? Megan, help me out.
It's the greatest integer to the left of the place that you're at.
Wow, that's perfect. Very nice. Very nicely said. You're going to be a math teacher, right, Megan?
I don't think so, but I
Oh.
respect what you do.
Oh, okay. All right. Okay, so here we go. So go back to this, and we're going to put -3. And we can check. And we're good. And now let's do letter D. So 2 times the x value plus 2, and that's a new looking grouping symbol here, but it actually represents a function, which is the greatest integer function. So, and Megan, what are we going to put here, of course?
2/3.
Mm-hmm. Now, do we take the greatest integer function value yet, or first simplify?
No, simplify.
Okay.
So it'll be 4/3 plus 2.
Mm-hmm. So this is 2 times 2, 4 over 3 times 1 is 4/3 plus 2. But to add fractions again, we need to have a common denominator. What can we always put underneath the 2, Megan?
A 1.
Without changing it? A 1. And now we want to have the same denominators so that we can add these together. So what's the smaller denominator, 1 or 3?
3.
So, well, 3 is the common denominator, right?
1, but we're going to use 3.
Yeah, 1 does fit into 3, right? Because 1 multiplied by 3 gives you 3. So what's the smallest number that that 1 and 3 fit into by thinking of multiplication? Well, 1 times 3 certainly gives you 3. So 1 fits into 3 through multiplication. 3 fits into 3 through multiplication, because 3 times 1. So therefore, the smallest number that 1 and 3 fit into by multiplication is a 3. And there's other ones, there's bigger ones, 6 and 9 and 12, and there's an infinite amount, but this one's the smallest one. And so what do we need to do? Well, 3 times 1 gave us the 3, so multiplying by 1 won't change anything. So you can just leave that the same, of course. And how did we get, by multiplication, how did we go from 1 to the 3? Well, times 3. So 2 times 3, of course, is 6. And now we can add these fractions together. And of course, we get what here, Megan?
10/3.
Mhm. And and now that goes right here. Well, we have to find the greatest integer of value of that 10/3. So it kind of helps if we change that fraction, or at least we got to figure out where that is on the number line. Otherwise, how are we going to know? So first of all, it's positive. And reducing 10 and 1, I mean, 10/3, how can we reduce that? How many threes fit into 10?
3.
3 times.
3.3.
Yeah. So 3 times 3 is 9, subtract 1. So the fraction value would be 3 1/3. And as Megan said, that's 3.3 repeating forever. So either way, we put that in here, whichever one you want to write. And now we find the greatest integer value of that. Any questions so far?
No.
And then Griselda, what's going to be the greatest integer value of 3 1/3?
3.
3. Very good. So this becomes incredibly simple now, I hope. Yeah? Yeah.
Yeah.
Okay. And that's what it should be. And 3. Okay. 2 more ideas, and that'll be it for the lesson. And now there's different ways to explain this next. There's like 4 or 5 of these, and they look kind of intimidating. And there's different, it's one thing for us to have to graph them without having anything to match versus matching them only. And because this is the, and for this moment in our math, I'm going to just teach you how to think of it by matching. And another time we could, if it was the next class or the next one after, we could graph it. Well, we can even do it here. If anyone wants to ask me, you can just ask me in the office hour, and I'd be happy to show you how to do this if there wasn't anything to match, okay? But I'm gonna show you at this level just how we can match them. And my explanation is gonna be a little bit just like my wacky road explanation and road signs was for the greatest integer function and how to understand that. I'm gonna start out by doing something a little weird like that as well. And I say weird, it's just meaning different. I don't really think it's weird. It's just, I think it's a way to make it understandable for people initially. So that's what you're about to hear from me here. So I'm just going to make up something that I think can help everyone have a better chance to understand this for the initial moments. So, okay, I'm gonna pretend that the domain axis
Mr. King.
is, well, it is the domain axis, it's the x-axis, but let's say, well, first of all, how many pieces do we have up here in this brace, open brace symbol? How many different equations do we have?
3.
3. The first one, how would we describe what this graph's gonna have to look like? If it's, this is y, h of x is another way of saying y. So y equals 4 minus x squared. Y equals 5 plus x. That's a second piece. Y equals x squared plus 1. That's a third piece. So what this piece look like? Well, first of all, how about the middle one? the second one. This is x to the first power. So Griselda, what's y equals 5 plus x gonna look like? What kind of graph is that?
A linear?
Linear, slanted linear, right? Two-dimensional linear because it's y and there's an x, huh? So it's a slanted line, isn't it? Yeah,
Yes.
it's like y equals 5 plus x. Or you could write it as y equals x plus 5. Isn't this that famous form, Griselda, y equals mx plus b?
Yes.
You see that now?
Yes, sir.
And what's the slope?
The M.
And what number is that on this equation? I don't see anything there.
It wouldn't be a 5.
Well, that's this one.
Oh,
What number is always in front by multiplication, even
One.
if it's not visible? So what's the slope equal, Griselda? What's the slope
One.
of this slanted line? 1. What does 1 mean? Increasing or decreasing line?
increasing.
Mm-hmm. What's this tell us?
5, which is the Y, the B,
The b, which is the y what?
Y intercept.
There you go. Okay. All right. So this middle one, we say, oh, that's a line. It just won't be, it doesn't get to draw. It's like the middle one is a line, but I'm going to start using some strange words here, but it doesn't get to graph itself forever because this domain axis has been divided up into territories like a, say like a continent or so I always wanted to be in a gang, you know, like to be a gangster, and like in El Paso or Chicago or whatever, and in the city they fight over what territory is theirs, huh?
Mhm.
And so this middle gang right here, it only gets to exist in a certain part of the city, in a certain part of this territory on the domain axis. And if it tries to go beyond that territory, watch out, because the parts of the city have been this way for some time now, and then we've had peace. And if I start to branch out beyond my territory, well, I'm asking for trouble, you know? So I know it sounds weird, right? So where is this second piece, Griselda? Where can it only exist? What part of this territory on the x-axis? Only between what and what along here?
-2 less than or greater than X less than 0.
And notice this one doesn't have an equal sign, does it?
Mm-mm.
And this one does, huh?
Yes, sir.
So if I'm on the x-axis, my territory starts where? Where does my territory start? I'm the leader of this gang right here, okay? And how much territory do I get along the x-axis? Starting where?
-2.
And so here's -2. Is that territory mine, -2? Well, it depends if there's an equal sign or not. Is there an equal sign?
Yes, sir.
So is this part of Mr. King's gang's territory right here?
Yes.
Yeah. And where does my territory continue? All the way on the x-axis. I guess I'm not a very good gangster because I don't get very much territory. Because where does it stop, Griselda?
That's 0.
And is 0 mine or somebody else's?
Somebody else's.
And how did you know that?
Because there's no line.
There's no equal sign, huh?
No.
Very good. And what kind of graph is my territory going to look like? Well, whatever this is. And what did we say this was?
1 plus 5.
Yeah, 1x plus 5, which is a line.
Mm-hmm.
Do you understand that?
Yes.
So my territory is only from -2 to 0, and not including 0. But hey, we fought for years and we got the -2 at least. Okay, and that graph, my I don't know, just pretend I'm trying to make something up here as I go. Pretend my on my my mafia family, our gang family, we have a logo and it looks like this equation, and it's a line, and it's a slanted line. So yeah, that's not a very, anyway, I'm just making this up. So what about the beginning? The beginning of my line is going to be at -2. And the end of my line is going to be at x equals 0. But in this part of my line, the beginning part is my territory. So I get to include this piece. So that's part of that territory is ours. But what about the end? Right here at 0. Do I get that territory right there, or is it somebody else's?
It's somebody else's.
So I'm going to put an open circle here.
Okay.
Does that make sense?
Yes.
And you're like, what is this teacher talking about, huh?
Mhm.
So now, so there's two things to think about, yeah? First of all, this is like the first mafia, the first gang, and where does it get to exist in this domain, or think of it, this as this city, Griselda? What X values? It better not go into my territory, which is -2 to 0, yeah, including -2 is mine. Oh, by the way, look at Griselda. What is this? This is the line, right? Isn't this from -2 to 0?
Yes,
And
sir.
it's a line.
Yes, sir.
And by the way, what did you say the slope was? Positive or negative?
Positive.
And that means a line going up, increasing.
Yes, sir.
And aren't all these lines here increasing?
Yes.
So far we can't cross out any or eliminate any of these graphs. So we're playing detective here, if you will. And it makes this, I hope it makes it kind of interesting. So what about right at -2, Griselda? Isn't that our territory? That my territory, Mr. King's mafia family? Yeah.
Yes, sir.
So that means what right here at the beginning of my line? Should it
A
be
solid,
empty?
a solid dot.
There you go. And then what about at the end of my territory? Is that point mine or no?
No, so it's an empty or open circle.
So that means it could be this graph, huh?
Yes.
This is an example of my territory, which is correct, huh?
Yes.
How about this one? Is there anything wrong with this one?
It's the opposite. So it starts with an open circle and then a solid circle.
Yeah, very good. So this one's out. Yeah?
Mm-hmm.
And he's like, why did I pick the middle one? I didn't have to. I just picked it because it was a line, but we could have picked anything. Okay, what about the one underneath here? William, are you with us? William, are you there? I think he fell asleep. No, I don't know what. Megan, what about down here? Is there anything wrong with this line?
The point at -2 should be solid, so
Yeah,
it's
you're
not
like,
going
well,
to
they're solid, but that's the other gang, isn't it?
be. Yeah.
Yeah. So this one's wrong. Oops. And what about this one, Megan?
Possibility.
That's a possibility. That's right. Very good. So far, so good?
Yes.
Okay. Now we pick whichever other piece. Of course, I'm not going to say gang all the time. I'm just trying to use it to make it real. I don't know if that's doing the job or not, but what about this first piece? Pretend that's the first gang family, mafia family, whatever you want to call it. And where do they get to exist, Megan?
Less than -2.
Less than -2, good. And so on these graphs, that means the first piece, do they get to exist at right at -2? Do they get to exist or not?
No, because there's no equals. So it'll be an open circle.
So that first family, -2, hey, that's my property. That's my territory. So they better have an open circle there. And that means that first graph, it better stop at an open circle because that was supposed to be my territory. Does that crazy way of saying it make sense, ladies?
Uh-huh.
Can you repeat that part again? I'm sorry.
What about?
The one where the 4 negative x squared.
Oh, so where does this function, this graph, by the way, and that's a parabola because it's y equals and there's an x squared. And remember, this is y equals. So y equals 4 minus x squared. That's y to the first power x squared. When one of them is to the first and the other letter is squared, that's a parabola.
Mm-hmm.
And because it's a negative in front of a multiplied, well, there's a negative in front of the squaring term. That means the parabola opens, which, well, x being squared means opening up or downward versus rightward and opening leftward. So when x is being squared, it's one of these two. And then which one is it, Griselda, if there's a negative in front? Is it opening up or down?
Up.
So up is when it's a positive number in front of the x.
Oh, okay. So it would be down.
Mhm.
It would.
It would be like this one, huh?
Mm-hmm.
So we know that the first family's logo or graph is going to be a parabola that goes downward. Now, if it had control of the whole city, well, then the parabola would just keep going forever. And it would look something like this. And something like this if it had control over the whole domain axis, the whole x-axis. But it doesn't get control over the whole x-axis. It only has control over part of it.
Mm-hmm.
So it's only going to be some piece of this graph. Yeah?
Yes.
And
Sir.
where does it have control, Griselda?
On x less than -2. But it is not doesn't have a line, so it's gonna be an open circle at one point.
Very good. So this is the first family, the first piece, and it's from -2 that way forever. And right at -2, it's not supposed to have that territory control, so that's open. This part here, it looks kind of like a line, but it's really like kind of like part of this. It's like this part, an open circle. So is this part okay so far, Griselda?
Yes, sir.
Yeah. And what about this one? Could this be the first family's territory? What's wrong with this?
No, because it does have a full circle and it's going up.
Very good. There's 2 reasons why this one's wrong. Plus, we already knew it was wrong because the middle piece wasn't correct.
Correct.
Is that okay?
Yes.
Megan, is that okay?
Yes.
And now, Griselda, is there anything wrong with this first piece?
It has a full circle or
Yeah.
solid.
And it's supposed to be what right here?
Open or empty.
Very good. So this one's wrong. And it was already wrong from the middle piece as well. And what about this one, Griselda?
That one is going up and it has an open circle.
So is the open circle part okay?
It is, but it's going up. It's a it wouldn't it be a positive? Oh no. Well,
Yeah,
it's
because
going.
this would be like a parabola that looks something like this. Part of this, oops.
Mhm.
And that would be the whole thing opening up, but they only have part of it. But is it supposed to, is this third, I'm sorry, is the first piece supposed to be a piece of a parabola opening upward or downward?
Downward, sir.
So that means this one is right or wrong?
It's wrong.
Mm-hmm. So this one is wrong. And by the way, we've already eliminated 3, haven't we?
Mm-hmm.
So it better be this one, huh? And weren't these 2 first pieces correct so far? Yeah?
Yes.
Is that okay, Griselda?
Yes, sir.
And what about this third piece? Okay, this is another gang, mafia, whatever you want to call it. And where do they have control, Griselda? Where on the x-axis?
0.
Starting at 0. Yeah. So at 0, should they have an M? Should their third piece? Here's the third piece. Third piece. Third piece. Third piece. This is all kind of, I don't know. Maybe is this too messy now? Do you want me to erase it, or can I wait?
You can erase it.
Okay. So what's going on with this third piece? Do they have control? They're supposed to have control at x equals 0, aren't they?
Yes.
And is this means what? Don't they have control? Don't they have a graph right here, a point?
Yes.
So this part
A
is
solid one.
a solid one. What about this one?
They do, but it's
Is it
facing
part
down.
of the third? Is it? Oh, yeah, you're right. But this has to be solid. And the solid point is on the second family. And is it supposed to be on the second family or the third family?
The second.
If this is an equal right here. So Griselda, what does this mean right here? If we pretend about the gang family, that means their territory starts where?
At
Does it-
X.
At X.
At
It's their territory are what X values along this domain axis line, starting
0.
where?
0.
And including 0, not including 0.
Including.
And how do you know including?
Because of the greater and equal to.
And do they just have control over one point and that's it? Just right there and that wherever, or is it also forever to the right?
Mm.
What x's are greater or equal to 0, Griselda?
Positive.
The equal 0 is right here. And where else?
Positive 1, 2, 3, 4. To the
So
right.
they get all this territory, don't they?
Yes, sir.
Including at x equals 0. Does that make sense?
Yes, sir.
And now what does their graph look like? What does their graph look like? It's this. And what is this, Griselda? When it's a y equals x squared plus 1. What kind of a graph is y equals x squared?
Parabola.
Good.
Up, facing up parabola.
Very good. But do they get the whole parabola or only a piece of it? Do they get this? Do they get this, Griselda? Here's the parabola, and they get it all throughout the city here. Do they get all throughout the city, and they get to have the whole thing everywhere?
No.
Just starting where?
At
what domain value?
0.
And so whatever the graph looks like, it's going to have a full point, and then it's just going to be this piece, huh?
Yes, sir.
So that means this part is not theirs. So it's just the part, sorry, It's the piece forever this way that opens up. Is that okay?
Yes, sir.
So now, that's what I was trying to show, okay? And I think it's easy to kind of get mixed up in the middle of all this, but let's look only at the third piece, or the third family, if you will. And we know it has to start at x equals what, Griselda?
0.
And then everywhere to the right, huh?
Correct.
And at x equals 0, if we look up or down and to find the mapping, that point better be what? Filled or empty? It better be what?
Filled.
Is this one filled?
Yes, sir.
And is the parabola opening upward?
Yes, sir.
So is that possibly correct then? I mean, is this third piece correct?
Yes.
Was the second and the first piece also correct?
Yes.
Yeah, so this is why this is the correct one. Is there anything wrong with this third piece?
It's facing down.
Good. That's one
And it
reason
has,
as well.
it looks like it has an open circle.
Very good. So there's two reasons why this one's wrong. And then not to mention if these are right or not, but just looking at the third piece, this is wrong, isn't it?
Yes.
And which graph has to be the correct one? When just one of the pieces are correct, or all three of them?
All 3?
Does that make sense?
Yes.
And we had already eliminated this before, but anyway, what about this one, Griselda? This third piece, is there anything wrong with this one?
No. Actually, it looks like, I'm not really sure because it's small, but it looks like it has an open circle.
That is an open circle, yeah. So would that make this piece correct or incorrect?
Incorrect, sir.
Good. And this one?
That would be incorrect. It started correctly, but it went downward.
Ah, very good. And so after we have investigated all three pieces, maybe we didn't even have to look at all three to figure out which one to match. But we did look at all three for learning purposes. And which was the one that is the correct one then?
A, or the first one.
So, any questions here, ladies? Or William, if you're there.
No.
Okay, and submit. And we click this one and it's telling us it's correct. Yeah, that doesn't mean this one, the one we picked. Okay, this one has three pieces again. This one only has how many pieces, ladies?
2.
Two. And this one has how many pieces?
2.
2. So how about we do this one together? But just real briefly, let's just do one piece here, and we might be able to know which one, at least eliminate some, and then I'll let you guys finish and the class finish the rest. Megan, which piece do you want to look at here of the three? You just pick one.
The third one.
Okay, the third one. And that's this one. So two things to look at, Megan. One, where is this function's territory, so to speak, or the gang family's territory? Where on the domain axis? Where do they get to start to have their territory?
At x is greater than 1. So at 1.
And so that means the third piece, the third family or gang, if you will, its territory is at x equals 1. Is that their territory at x equals 1? Should there be a filled point on the graph of this third piece or an empty point?
An empty point.
Because whose territory is that x equals 1, Megan? The first family, the second family? Which one has control at x equals 1?
The first one.
The second.
Positive 1, Griselda.
Oh, the second one.
Yeah. Who has control over x at x equals negative 1?
The first one.
The first one. Okay. Does that make sense?
Yes.
Griselda, who's in charge at x equals 0?
X equals 0. X. I guess the middle one.
The
I'm
middle
not
one.
sure.
Because negative 1 to 1 isn't 0 in the between part.
Yes, sir.
So 0 belongs to this territory at x equals 0 belongs to the second piece or the second game. How about x equals negative 4, Griselda?
I don't know.
So who has control right here at x equals negative 4?
Actually, would be the middle again, wouldn't it? Because of the.
So where are the numbers, Griselda, from negative 1 to 1? Where would that be on the domain axis? Let's say I come over here and negative 1 to 1. So where is this middle family, this middle piece? Where does it have control? Does it have control at negative 1?
Not necessarily.
Not necessarily, or no? Is there an
No.
equal sign right here?
No.
So here, no. I'm just drawing where they have control.
No,
Not
they
at
don't.
negative 1. That's open.
No.
And what about this way? Who has control? Who does have control at negative 1, Griselda? Not the second family, but which family?
The first one.
The first
Which
one
is
has.
X.
And what about anything left? Whose territory is that? Whose territory is all this?
It's greater than. It would be the the second one, wouldn't it? Because of the X, the less than and greater than 1.
I think the trouble you're having, Griselda, is what a lot of people have trouble with is in just remembering what these inequality signs mean. So what does the tip mean, Griselda, on an inequality symbol? What is that's supposed to be a tip right here. The
Less
tip
than.
points to the smaller side. So what does this mean right here if the tip is pointing to the X? The X is what? The larger or the smaller object?
The smaller.
So all X values that are smaller than whatever objects over here.
Then negative 1.
So what X values are all smaller than negative 1? Where on this domain axis?
All negatives. So negative 4 would be included.
Very good. And what else? All of these.
Negative.
Huh?
Yes, sir.
So that's
so
what I think you were not thinking in the right way when you saw all these inequality signs. And I think that's what's throwing you off. Okay. Who's in control right at negative 1 on the x-axis, Griselda? The first graph, the second one, the third one, which one?
It would be the first one.
So that means the first piece better, when you get right at negative 1, the first graph better have what? An open circle, which means they're not in control, or a filled circle?
A full circle.
Very good. Who's in control from negative 1 to 1?
1 to 1.
What does this mean right here, Griselda? This means what? The tip's pointing to what object?
To the negative 1.
So this means negative 1 is the smaller object compared to the x values. And these X
So-
values are also, there's another tip, and that means this X is smaller. So the X values that are smaller than what?
Then
What,
positive, one.
one.
Positive one.
So where on this x-axis, this domain axis, are numbers that are smaller or equal to 1, but also these x values have to be larger than -1. Because remember, this means -1 is smaller than the x values. -1 smaller than the x values. Another way to say that is that the x values have to be bigger than this number over here. So,
Okay, so it would be to the right.
so from -1 to 1, who's in charge of this territory? The first graph, the second, the third?
The second.
Mhm. And who's in control right at -1? Is it the first graph, the second graph?
The first one.
Because
The less than or greater than.
this equal sign right here. And who's in charge right at 1? +1, Griselda.
The second one.
Ah, very good. So that means wherever their graph is, the mapping at x equals 1, it better be what? An open circle at +x equals 1. Should it be an open circle or a filled circle?
A filled circle.
And what about at -1 for the second graph, for the second family?
It's an open circle.
There you go. Are you getting it?
Yes, sir.
And what about the third family, the third piece? Where is its territory? So this is the territory of the second piece from not including -1, but including 1. That's the green one. The first family is this purple part, but not, but including, it's kind of hard to represent. This would be a bracket because the purple is the first one and it includes -1. And what about the third piece? Do they have control at x equals 1 or not?
No, sir.
So this third piece better start with what at x equals 1? A filled circle or an open circle?
Or open circle, sir.
Now you got it. So now it's just a matter of, well, what are these pieces? What's this first piece, Griselda? If it's y equals 3x plus 1, that's first power.
It's
First
a
power.
linear, a line.
Good. So the first piece better be a line, and they all are. But and the slope is, what kind of slope is this? Mx plus b.
3.
3. Is
positive.
that a positive slope? So
Positive.
it better be a positive increasing line. So let's see if we can eliminate anything. So we collect ourselves and our mind. And what did you tell me was going on? Who's in charge at x equals -1? Which group? Which graph?
The first one, sir.
So at -1, the first graph, which is a line, and it was increasing line, which this is, but what's wrong with this piece right here? What's happening right here at -1?
It's an open circle.
And they're supposed to have that territory. This was supposed to be what?
A solid circle.
Solid. So is this one right or wrong?
Wrong.
What about this piece?
That's going downward and it has an open circle as well.
So is this one correct or incorrect?
Incorrect.
For 2 reasons, huh?
Yes, sir.
How about this one?
Up and solid. So that could be a possibility.
And this one?
Also a possibility.
Mm-hmm.
It has both. But the the parabola has I'm not sure because it's kind of small, but it looks like it's a solid circle on the the first one to the left, to the bottom.
This one?
Yeah. Is it an open circle? I can't see it.
That's
It's
open.
open.
Oh, it's open? Okay.
And so
So
is
then
that
this
one.
one. Oops.
And where does it end? It ends with what? Open or solid?
Solid.
And this one too, huh?
Yes, sir.
And isn't that what's supposed to happen with the second function? Are they supposed to have the territory at x equals -1 or not?
Mm,
No.
no.
Is there an equal sign here, Griselda, on the -1?
No.
So
So
do
it
they
has
get
to be
control at
open
x equals
circle.
-1, or was that the first group?
Just the first group.
So
So there has to be an open circle at the beginning of the parabola,
Mhm.
and
What
then a
about at the end?
solid circle has to be full.
Very good. So that's still, so that this one's still okay. Open,
Yes.
filled. Open, filled. We already
Yes.
crossed these two out from looking just at the first picture.
Yes.
So what else? What kind of parabola is this one, Griselda?
It's upward,
And this one?
downward.
And what tells us up here on this second equation if it's opening upward or downward?
It's a positive square or x squared.
In front of the x
So it's
squared,
the
the
3.
yeah, and that's positive.
Yes, sir.
So that means the parabola opens which way?
Up.
So is this one opening up?
Yes, sir.
Is this one?
No.
So that means this one's wrong, huh?
Yes, sir.
So what's the only one left?
Just the C,
Yeah.
which is
But let's just look at the last piece just for learning's sake. Who's supposed to be in control at x equals 1? Which graph? The first, the second, the third? Which one is supposed to be in control at domain value x equals 1? The third one or the second one?
the second one.
Because of this part right here, x less or equal to 1. And then this one is only in control for all x's that are larger than 1. Yeah, the tip is pointing to the 1. So 1 is smaller object compared to the x. So that's a way of saying the x values then are larger than this object, larger than 1. So when you go, when you go to 1 and to the right, the third graph is not in charge at x equals 1, but it is in charge. It does have a graph everywhere else. So right here at x equals 1, this third piece, Griselda, is this supposed to be
Open circle.
And it is, isn't it?
Yes, sir.
Yeah. And the parabola is supposed to open which way? By this equation right here.
Downward.
Because?
Of the negative before the x squared.
Very good. So this is downward, and so is this one, and so is this one. This one, no. But they're not supposed to be in charge, so it's supposed to be open, and that one's open, and this one's not. So that one's wrong, that one's wrong. So yes, it could be the third piece is correct on both of these, but we've already eliminated this possibility because it was wrong on the second piece, but it was correct on the first piece. But this parabola, this middle one, was wrong. You remember? Is that okay?
Yes, sir.
So then it has to be this one. Any questions there?
No.
No.
So that takes some patience. I know you're starting to get tired, or you're already tired, but I hope that makes sense. And we click it. And we are correct. So very good. Okay, So we did 2 there. You guys can do this one, matching again, but there's only going to be how many graphs here? How many pieces?
2.
Only 2. And the territory is split up because there's only 2 families in charge. They're split up. And where is their territory split at? Right at what X value?
3.
3. Who gets whose territory is it at X equals 3? The first
first
one, the
one.
second, which one?
The first one, sir.
Very good. Okay, so let's just do this one because we actually need to graph it on the tool. How many pieces are there?
2.
2. This is y equals x to the first plus 5. Y equals 1/2 x to the first minus 2. So, Megan, these 2 graphs are both what kind of graphs?
Slanted lines.
Slanted lines. Very good. And where is the dividing point of their territory? Where along the domain axis here?
At -6.
At -6, so good, which is right here. So this is where the territory split. Well, that must mean someone, I guess it's possible they could say no one's in charge at -6 and there would be open points on both territories, but they are not doing that to us. They're saying one of them's in charge. One of them has the territory right at -6. And Megan, which one has the territory right at -6?
The first one.
The first one. So this first graph, which you said is a slanted line, when we get to 6, it better be what? Open circle or filled circle?
A filled circle.
Filled circle, good. And the second graph, which also is a line, and it's gonna kind of start at x equals -6, but with a filled circle or an open circle?
An open circle.
Does that make sense, Grisela?
Well, I understand like the beginning, like when you guys are doing the dots, but how do I know where to place is it the beginning of, like, say the first one, x, it looks like x plus 5, and then
Good.
comma x less than or greater than -6. So I'm assuming we start with -6 and then go up 5.
Okay, so good question. So here is the equation of the first piece, Griselda, right?
Yes, sir.
And what kind of equation is this? This is like y equals what?
Line, a linear, ymx plus b.
And and that's a line, that's a slanted line, isn't it?
Yes, sir.
And we need 2 points to draw a line, or we can use the slope and the y-intercept, but we got to be careful because at x equals 0, normally you would just put 0 in and get a point and then pick another one, but that's when there was only one equation. And the graph was, they had this complete territory, so the graph would just go on forever. But does this first slanted line, does it get to go forever, Griselda? Or does it only get to graph part of itself? Is it gonna get to go forever? 5 is right here, the y-intercept. The slope is 1, so you could say 1/1 is rise over run. You could go up 1.
So forever.
So it would be forever. It would be forever if there were not 2 families fighting over this territory, yeah? So does this first graph get to graph it forever? Which means all these x values it has control over, so therefore it has its graph. And all the x values this way it has control, so it gets to graph its whole line, or is it only going to be a part of this line?
Up till 5? And
So
then to the
the-
forever on the negatives.
So tell me, Griselda, where along here does it have control? Where along this x-axis? Start. So, and that's this first piece.
Uh-huh.
So at -10, for example,
Starts at -6.
-6. So I think it'd be a good idea to figure out a point at -6. Yeah.
Mm-hmm.
And now we put -6 into that equation, and now we can find out. So x plus 5. So instead of x, what are we going to put there, Griselda?
-6, sir.
And what is -6 plus 5?
-1.
So a point on this line is, one of them is -6, -1. So let's pretend that that's like right here, -6, -1. And that's this point right here. Yeah?
Yes, sir.
Now, do we get to make this a filled point or an open point? Well, it depends who's in control right at -6. One of these is in control.
The
Who
first
gets-
one.
Which one?
The first one.
Very good. So that means this is going to be what right here? Filled, open, which one?
Field, sir.
Filled. And then which way does this graph get to continue? Does it have control when you go this way on the x-axis, which means you could graph all this part? Or is it only in control when you're going to the left?
To the
Okay.
left.
So they only get this piece. Excuse me. So that's the first graph is only this part from here this way. I'm messing it up here, but so that means, should we keep this part of the line, Griselda, or do we have to erase this part?
Mm,
This part.
we would have to erase it.
Yeah, because they're not, this first graph does not get to show itself on this territory, does it?
No.
Who gets to show itself on this territory when you move past -6 this way? The first graph or the second graph?
It would be the second,
Oh,
but an open circle.
good. Okay, good. Open circle. And then if I try to erase this, it's going to erase the whole thing. So we're going to come back over here.
Mm-hmm.
So we're going to have the computer. So it's the first piece is a line. And oh, I guess we get to, no, I don't know if that'll work. I've never graphed it myself here.
I think it's gonna be the middle one, no?
It might be. I guess we'll find out. Okay. So but then we got to tell it filled or open as well. So yeah, I'm surprised. I don't remember ever doing this. I just know how to do it myself. But on this tool, I'm not sure. So what did we say the point was where this piece is going to end? The first piece, it's going to end at -6,
Six,
-1.
-1.
So that's right here, huh?
Yes, sir.
So I don't know what's going to happen. I'm sure it's going to fill a point right there. So there's one point. And then we need one other point to make the line. Now, does it get to have a graph this way, Griselda?
No, sir.
So we got to pick a point this way, don't we?
Yes, sir.
So we can either pick a
So-
point by using the slope and counting, or we can just pick another number on our table. So I don't know. Do you have a preference, Griselda? I keep picking on Griselda here.
-6
Well, we
with
already did that one.
-3. Or
So does the first graph get to graph itself at x equals -3?
no.
Where?
It starts at -6. So anything after, so -8,
Okay. So
-8, -4.
So what's -8 plus 5, Griselda?
-3.
So that's another point. -8 and -3. And graph that. But what's supposed to be right here? I'm not sure of how this is going to work, but was this supposed to be filled? Oh, it is supposed to be filled, yeah, because there's an
Yes, sir.
equal. So
Yes,
then
sir.
that's, maybe the computer knows what to do and it would have made it empty. I don't know. We're going to find out on the second piece. So now let's do the second piece. So the second piece is going to be at x equals -6 also, but it's going to be what, Griselda? Filled or open?
Open, sir.
And then we need to make, good, we need to make a table with 2 points for that as well. So and this one is y, well, I'll write it here. So 1/2 times x -2. And so we just got to figure out what x's we want to put in. Well, it does make
would be-
sense to start at -6, but we know it's going to be what? A fill point or an open point?
Open.
So then I hope you understand it makes sense to start at -6, but because that's where the graph, the second graph's going to start. Now we need to get its mapping. So we're going to put -6 in right here for x and then compute. So what's positive times negative, first of all?
Negative.
Ne-
And Megan, what's this 1 times -6 divided by 2 going to be?
-3.
Minus 2 more?
-5.
So at -6, we get -5, but this point right here is going to be what, Megan? Filled or open?
Open,
Open, because?
because there's no equals sign.
Very good. So now we're going to go back to, well, let's just get one more point before we go back and graph it. So Megan, what would be another point we could pick? Can we pick a point to the left of -6, or does it have to be greater than -6?
It has to be greater than -6.
Because?
Because in the original function, x is greater than -6.
Very good. So give me a number that's greater on this x-axis than -6. Just pick one you like.
-1.
Okay. And now we plug it into this equation again. So it's going to be y
I
equals,
guess I could have picked 2, huh? It's easier.
put a what in? A 2? Is that what you said?
Yes, sir.
Yeah, I said I guess I should have put a 2. It would have made it easier.
Well, it's too late. You already said -1. I'm just kidding. So 2.
Mhm.
What's even easier than 2?
0.
0. Yeah. So how about that? But that's good you thought of that, Megan, that because otherwise with a 1, it would be a fractional answer instead of a
Fraction.
nice integer, right? Good.
Yeah.
Well, I'm glad that you realized that. That's good thinking. Okay, so what is 1/2 times 0, Megan?
0.
Minus 2.
-2.
So we get the point 0, -2. And that's a second point, and but the line goes on forever, and we're just trying to get a second point. So we come to our graph, and we click line, and now, so that answers our question. Oh no, I guess it did show this last time. And it was actually going up even though ours went down. It doesn't show an open circle or anything. So we're gonna find out if it does it correctly or we have to change it, okay? I'm guessing that it's gonna know it already. I don't know. We'll find out. So where are we gonna start here, Megan? At what happens right at -6 for the second piece? What was our point?
-6, -5.
Good, and now comes the magic moment. What do you think, Megan? Filled or open? You think the computer is gonna know? You think this graphing tool is gonna know, or it's gonna be filled?
I think it's gonna fill it.
Yeah, well, you're probably right. And now, what's the other point that we know?
0, -2.
Now is the magic moment. Well, maybe they fixed itself here. I don't know. And there it is, but it's still filled, isn't it? And it needs to be open. So I'm hoping ray 1, ray 2, isn't it the second ray that we need to make this open? So I've never done it before, but I hope when I click this, it gives us a choice. Remember how we did it with inequalities and you'd click it over here and it would give you dashed or solid or something? I'm hoping that's what happens right here. Well, let's find out. And yay.
Oh, yay.
It does. It tells us the 2 points that we picked. And notice here, I don't know if I'm mistaken or not, but I think it shows it right here because this is the point that we need to change, huh? Not this one.
Yes.
So we just click this one and there you go. Well, that's pretty cool. So I never did that before. If I did, I've already forgotten that I did it, but I don't know. But anyway, does that make sense, ladies?
Yes, sir.
Yes.
So yeah, so there's graphing pieces, a function that it has not just one part or one piece, but it has 2 or more. These are called, the fancy name for it is piecewise functions. Piecewise, and that means there's more than one piece, 2 or more. And let's check it. And check. And we are correct. Very good. Any questions here?
No, sir.
No.
Okay, well, we made it to the last piece. And the last piece, I've really taught this to you before, at least this part of it. So that's hopefully good news. So let's just do a couple of these and then we're done. So this one, we can change g of x to y. You don't have to. So we, at the beginning of this assignment at the top, it asked us to recognize what kind of function it was. And some was a linear, constant, absolute value, cubic, squaring, square root. And then we learned this new funky one, the greatest integer function. And so now it helps for us to be able to recognize what kind of function this is coming from, what kind of general function. And what does this stand for, right? This is not the greatest integer with the highway and the integer road signs. This is just what?
Absolute value.
Good. And absolute value graphs always have, well, we could show you here. absolute value graphs always, I mean, we could just graph it and we wouldn't have to be thinking at all, but that's not the point of this lesson. It's for us to be able to recognize something, and that is the following. The absolute value graph without any changes being made, meaning there's no plus or minus inside a number inside this or outside, then the graph, the standard absolute value graph looks just like this. It comes together at 0, 0, and it really is like one half of a line here that decreases and then another half that increases. Now, if we make a change by adding or subtracting, so if we add a number or subtract a number inside with the x, then that's going to move the graph that you have left or right. And it does when it's inside with the x. If you say +2, for example, it doesn't move this whole graph to the right 2 units. It moves it the opposite way. So if we say +2, which I'm about to type, this graph right here is going to move everything's going to move 2 units that way. So this little point, vertex point right here, where the 2 pieces come together, it's going to move right to this part. Does that make sense, ladies?
Yes, sir.
And then
Yes.
the right piece is going to go up and the left piece is going to go that way. Yeah. So I'm going to type +2. Is that part okay?
Yes.
Yes.
You kind of remember we had this discussion before in the classroom back before life changed on us, yeah? And now what do you think happens if we do that again? Oops. What if we put here, Grisel, the -4? What's that going to do to the graph? What's it going to do to the blue graph? What if I erase that one? What's it going to do to the blue graph, Griselda, if I put a -4?
It'll move to the right.
Huh?
It'll move to the right.
Good. How many units will it move? If I
4.
if a 4, yeah. Is that okay?
Yes, sir.
Okay. What if we instead put this graph again, but put a -4 not inside with the x variable, but outside? Now it's not going to move left or right, but up or down. And when it's the up or down movement, if you write it over here, if you write it on this side, well, then it does the opposite. But if you leave it on this side, which we have to because this, well, I don't know if we have to, but here, I'm just going to put it here. So the -4 is not inside with this x variable, so it doesn't shift the graph left or rightward, but up or downward with respect to the second dimension, and it does what it says. So what's going to happen, Megan, if I put -4 outside of this absolute value? It's going to move it which way?
Down 4.
Mm-hmm. And there it is. Is that okay, ladies?
Yes, sir.
Yes.
And what would happen if we put, Griselda, say we put here a +2?
It would move up
Upward,
2. Up
2.
2.
And there it is. It's the original graph, but moved up 2. Is that okay?
Yes, sir.
And this works, if this is an absolute value graph, this idea of moving left or right and up or down, which is the fancy word is a shift, or a translation is fancier yet. Translate means shift, left, right, up or down. And it wouldn't matter if this was a square root instead, it would just not be this shape, it would be another shape. But it would still move left or right or up or down the same way. One more thing before we go back, and then that's it, is what if we do both two types of shifts? So we do it on the inside. Let me clear these out. So if we put here, let's say we put, say, a +3, what's that going to do, Griselda, if you put a +3 inside?
It's gonna move it to the left.
Mm-hmm. And then I took a little rest. Oh, I don't want it to be the same color. So +3. Take a little break. And now I want to make a change. Megan, what do you want to do? Move it up or move it down? You tell us.
Down 2.
So then what do I have to type right here if I want to move it down 2? When it's the y dimension.
-2.
Very good. Okay, you do what? So here it actually moves like you would think, and it does down 2. Is that okay, ladies?
Yes, sir.
Yes.
Does this sound familiar from what we did earlier in the semester?
Yeah.
But it may or may not have been an absolute value. But we didn't talk, I can't remember how much we talked about it. But anyway, as long as we understand. So now we're going to go back to the homework. And so now I hope, as long as you know what the original graph looks like, then this part should be easy to pick. So Griselda, this one is the absolute value graph, which is the one that is in the one that comes down here to 0, 0 and then goes up. But what's this going to do right here, Griselda?
It's gonna move it down. Go down
5
to
units
the,
down, huh?
yes, sir.
So then we got to match it is all. So which one of these looks like it's moved downward 5 units?
The first
This one looks like it's moved what, Griselda?
to the left,
And this one?
to the right,
And this one?
up,
And this one?
down.
So which one does it have to be, of course?
First one.
Mm-hmm. And check. Any questions here?
No, sir.
No.
So the only thing left is if we don't know what the original graph looks like. And so the square root graph, and if you ever forget, you can always go to Desmos or something and just type. Oh, you know what? I forgot what the darn square root graph looks like. Oh, there it is. And now if I make a change, add, subtract, it'll either be inside, moving it left or right or up or down and so forth. So the one I want to show you is one we've never, well, I don't remember for sure, but if we have, it's not been very often. And that's the reciprocal graph. And this is the very basic reciprocal graph, 1 over x. And now they're going to ask us if we change it here somehow by adding or subtracting. So if we did this, what if we put a change right here next to the x? Let's say we wrote a -2 here. Megan, what's going to happen if we put a -2, and you can put it in a parenthesis down here if that helps us, or not, as long as it's next to it here. Oops, I messed that up. So let me put it here, x, and then here, let's say we put a -2. What's going to happen, Megan, if we subtract, if we put a -2 inside next to the x, not outside by itself, not up here, but -2, but down here with the x. Wherever the x is, you put it right inside. So that's going to move it left or right words. But what do we do then, Megan?
Is it still gonna be the opposite?
Mm-hmm.
Okay, so it'll move it to the right too.
And both pieces, yeah?
Yes.
This piece and this piece is all gonna shift over too. You see this part right here, ladies? There's no graph right here at x equals 0. That's this vertical asymptotic behavior, and that's because at 0, if you put 0 right here, 1 divided by 0, I mean, we had this discussion once or twice, but 1 divided by 0 was undefined number. Remember when we kind of talked about that?
Yes.
Vaguely or remembering. And then, so that means at x equals 0, there is no mapping, which means it's not, this x equals 0 is not in the domain set. So there's no mapping, no graph. And that's when you get, on one side, the graph gets closer and closer, and on the other side, it gets closer and closer, but never touches right there. And so, and I guess it would be nice if it was a different color, but this does it. Oh, I think there's another place you can change the colors. But anyway, so at x equals 0, there is no mapping. So as we come in here, all these x's are the first numbers, and those, that point there is part of the domain set. But if you get closer and closer to x equal to 0, it'll never make it there, by the way. So now we're going to move everything. We just said 2 to the right because I typed y equals 1 divided by x. And I think I said minus 2. And that meant it's going to move. This blue graph has been shifted, both pieces 2 to the right. So instead of being undefined right here, instead of, and let me just draw that, x equals 0 is where this one was undefined. But now this undefined vertical asymptotic boundary line where there's no mapping is also going to get shifted over. So if I graph x equals 2, and that's where the new graph is not going to be defined at x equals 2. And that's why these two green pieces are getting closer and closer on this side and closer on this side. So I hope that makes sense. So what happens when we go back? And so I wanted to look at, for example, this one. So Megan, what's this one going to be? It's the reciprocal graph, which is coming from 1 over x, which is this piece. It looks like.
So it's going to move it to the right 5 on the x-axis.
And I messed up here. Sorry. Say it again. It's going to move it what? 5 to the what?
5 to the right on the x-axis.
Good. So instead of the vertical asymptote being right here anymore, it's going to move 5 units to the right. So this vertical asymptote is going to be at x equals 5. That looks good, doesn't it?
Yes.
Wasn't the first piece going down like this and the second piece was this kind? So that's good. What's wrong with this one, Megan? They moved it which way? Not
They
to the
moved
right.
it to the left 5.
Yeah. And what does it look like they did here?
They moved
didn't
it
move
up
it
5
left
on the
or right.
y-axis.
Yeah, good. They moved it up, didn't they? And what did they do wrong here? They moved it what? Not up, but
Down.
what? Down.
Down.
Mm-hmm. So therefore, which one is the correct one then, Megan, did you say?
The first one.
Mm-hmm. And one more. And then we'll stop. I know it's been too long, and I don't know what to say. Here I was thinking I was going to be able to do 2 sections, but I don't know. So what about this one right here? It's coming from 1 over x. What's this part do here, Griselda? The x plus 3, it moves the graph which way? Griselda, are you there?
Yes, it's because my son is having his therapy session to start, and we're trying to connect him onto another laptop.
Oh, I'm sorry. Well, let me just finish this little piece. Last thing. So this is normally what 1 over x looks like. So the plus 3 is going to move these 2 purple pieces, and it's going to move them which way? If it's plus 3.
To the negative side, to the left.
So it's going to move these 2 pieces 3 to the left. And then this part is going to be the y translation. And then you do what it says. So it's going to move the graph, this graph 3 to the left. And then what?
I'm sorry. It's
Down
because
3 or up 3?
Up 3.
You do what it says here, up 3. Okay. So which graph looks like the correct one if you take this one, move it 3 to the left, which by the way means the vertical asymptote is going to be at -3. So this one looks like they moved it to the right. So that's wrong. This one also is moved to the right. This one is moved to the left 3, and so is this one. But which one of these 2 did they move it up as well? Move it up. The first one, the second one, which one did they move up as well? 3 to the left and then up.
The first one.
Mm-hmm. So, and then check. And we are correct. Is that okay, ladies? I know that's a little bit rushed, but that was something we've already talked about in the past. So is that okay?
Yes,
Yes,
sir.
sir. Thank you.
Okay, you're welcome. So the only thing left is doing the same thing with the square root graphs, the cubic graphs, the parabolas, and lines, but no, you don't have to use, not that one. So, but you should remember what the parabola looks like, and then it shifts. And the cubic graph, you can always go to Desmos and graph the cubic, but it looks like this. And then you just decide which way is it moved. Is that okay?
Yes, sir.
Yeah.
Okay. Okay. So, well, that took a long time. I'm really sorry. I don't know what to do about this, but I'm trying to make it so you all can actually learn it and have a fair chance. But so I hope that's happening, and especially you two. You've been very good about being in the class, and I thank you for that. And I hope you're doing well. And it's always going to be available on Blackboard, but I hope you'll keep joining, and I thank you for your patience, okay?
Thank you for helping us, sir.
Mhm.
Thank you.
You're welcome. Well, have a good day, and I hope to, there will be an office hour tomorrow from 10:50 to 11:20 if you want to ask a question. Otherwise, I hope to have you join in on Thursday, same time, okay?
Thank you.
Okay,
Mhm.
thank you.
Okay, you're welcome. Have a good day and goodbye.
You too,
You
sir.
too. Bye-bye.
Bye.